The physical limits of charge-based electronics dictate a hard ceiling for computational speed. As we push devices to operate faster, the electron stream loses phase coherence, scattering through the lattice and destroying the data signal. Standard ferromagnetic transition metals used in conventional spintronics hit a rigid operational wall at gigahertz switching speeds. Bypassing these limits requires a different atomic substrate, the heavy elements of the rare earth series. The structural advantage of a heavy rare earth atom is its electron configuration. The 4f electron shell is deeply localized, physically shielded by the outer 5d and 6s shells. Because they are isolated, their intrinsic spin states remain undisturbed, creating massive, tunable magnetic moments. The second advantage is their high atomic mass, specifically for elements with an atomic number, Z, greater than 56. In physics, the strength of spin-orbit coupling scales proportionally to the fourth power of the atomic number. Engineers utilize this specific atomic architecture, shielded magnetic moments, and intense relativistic coupling to construct three distinct quantum states: half metals, topological insulators, and compensated ferrimagnetics. Heavy rare earth elements possess the magnetic magnitude and coupling strength required to break conventional spintronics. To build a functional spin-based circuit, the injector must generate a current where exactly 100% of the electrons share the same spin state. Crystalline quaternary Heusler alloys provide the framework for this absolute spin injection. We engineer these alloys to achieve half metallicity. This creates a continuous conduction band for one electron spin channel, while opening a distinct energy gap for the opposite spin channel at the Fermi level. Rare earth 5D conduction electrons mediate exchange interactions that lock the lattice into this state. We can observe this empirically in the calculated data for specific compounds, such as lutetium, cobalt, vanadium, aluminum. This density of states chart tracks available energy states. The spin-up channel shows continuous metallic conduction bands crossing the zero energy mark. Contrast this with a spin-down channel. A defined energy gap exactly at the Fermi level entirely blocks conduction. This absolute band asymmetry ensures that only a single spin state acts as a charge carrier. By engineering the lattice with rare earth elements, we lock in a half-metallic state that functions as an absolute 100% efficient spin filter. Generating polarized currents is the first step. If spins scatter during transport, the data is lost. To protect the spin state, we most transition the material into a topological insulator phase. The intense spin-orbit coupling of heavy rare earths forces relativistic band inversion, pushing the valence and conduction bands past each other. This inversion makes the bulk of the material a struct insulator, while forcing conductive, spin-momentum-locked states onto the surface. These surface states are robustly protected by time reversal symmetry. Achieving the quantum anomalous Hall effect requires breaking that symmetry. This opening of a gap at the Dirac point allows for one-way chiral conduction. Traditionally, researchers used bulk magnetic doping to achieve this, but it introduces structural disorder and scattering centers that degrade electron mobility. An advanced alternative is the magnetic proximity effect, layering a topological insulator with a rare earth ferromagnetic insulator like europium sulfide. Its uniform exchange field penetrates the adjacent layer, inducing an interfacial gap in the topological surface states without disrupting the lattice. The gap creates one-dimensional, lossless chiral edge conduction. Massive rare earth spin-orbit coupling creates topological protection through band inversion, providing the proximity field needed to engineer lossless chiral pathways. Active memory operations face a hard speed limit. How fast can we flip a magnetic bit? Standard ferromagnets are physically constrained to the gigahertz regime. We bypass this constraint using fully compensated ferrimagnets, such as the rare earth transition metal alloy gadolinium iron cobalt. Internally, the 5D spins of the rare earth interact antiferromagnetically with the 3D spins of the transition metal at the Fermi level. Because these sublattices have differing angular momenta, we can reach a compensation point where they perfectly cancel each other out. This data shows the effects of optical femtosecond excitation acting on the alloy. The transition metal sublattice demagnetizes rapidly, falling off within just 0.2 picoseconds. Meanwhile, the rare earth sublattice takes nearly 10 times longer, a full 1.5 picoseconds, to demagnetize. This differential in rates forces a transient, non-equilibrium state where both moments briefly align. This transient state allows for magnetization reversal in the terahertz regime. The antiferromagnetic pairing of these non-equivalent sublattices allows for the manipulation of transient spin states, shattering the gigahertz speed limit to reach terahertz scale MRAM. Charge-based electronics are arriving at their absolute physical scaling limits. A viable spin-based computational architecture requires three uncompromising solutions: perfect polarization, lossless protection, and rapid switching. Half-metallic rare earths provide the solution for perfect spin polarization. Topological insulator proximity heterostructures provide the solution for lossless spin transport. Compensated ferrimagnet dynamics provide the solution for terahertz switching. These three solutions share a single physical origin: the highly localized 4f orbitals and intense spin-orbit coupling of heavy rare earth elements. Heavy rare earths are not merely an iterative material improvement, but the indispensable physical substrate required to build high-density MRAM and quantum computing architectures.